you so much for the introduction. So in this talk, I will present our work that uses safety properties to generate vulnerability patches. So first, I will discuss some background information on software vulnerabilities and automatic program repair. Then I will describe safety property and how we use safety properties to generate vulnerability patches, which involves synthesizing patch predicate and optimizing patch location. Lastly, I'll present our evaluation results and conclude. Software vulnerabilities continue to be a rampant problem. Last year, over 16,000 vulnerabilities were reported. Among them, 25% are well-known vulnerabilities, including buffer overflows, bad typecast, and integer overflows. So far this year, 3,000 vulnerabilities have already been reported. When a software vulnerability is discovered, the software vendor will need to develop a patch and release the patch for the vulnerability, after which users can apply the patch to fix the vulnerability. Because releasing the patch takes time, there usually exists a window of time between the discovery of a vulnerability and the release of a patch, which is called a pre-patch window. During the pre-patch window, attackers can exploit this known vulnerability because the patch is yet available. One study published in 2016 finds that the average pre-patch window is as long as 52 days. In order to reduce the pre-patch window, many automatic program repair techniques or APR techniques have been proposed. Some of them leverages fixed patterns to mimic developers' patches. Some uses genetic programming to generate patches. Some generate patches by borrowing code from correct programs. Others uses symbolic execution and constraint solver to generate patches. However, state-of-art API techniques have two major limitations when they are used to generate vulnerability patches. First, the correctness of the generated patches is heavily dependent on the completeness of the test suite they use, because they generate a large number of candidate patches and then rely on the test suites to determine whether a candidate patch is correct or not. If the test suite is incomplete, an incorrect patch can pass the test suite and mistakenly be considered correct. A study published in 2015 confirms that most of those previously considered correctly generated patches by state-of-art API techniques are indeed incorrect due to this limitation. So now we show one patch that is incorrectly generated by state-of-art API techniques. This patch removes a check to integer overflow in the code of libtip in an attempt to fix an integer overflow. Due to the incompleteness of the test suite, this incorrect patch would simply not trigger the test input that would reveal the integer overflow, and thus will be incorrectly considered correct. Second, these API techniques are not designed to address complex vulnerabilities involving interprocedural code, because they focus on generating candidate patches for a single function. For simple code, like this example, where the allocation of the buffer and the access of the buffer occur in the same function, they may be able to generate a patch that would check whether the range of access is within the bounds of the buffer. However, they cannot generate the correct patches when the allocation of the buffer and the access of the buffer occur in different functions. The example is the result of breaking down the previous example code into 3 separate functions. Function G allocates the buffer. Function H accesses the buffer. And function F calls G and H to allocate and access the buffer. This is a common pattern that exists in complex and large applications. The challenge is that function H has no information on the size of the buffer. Function F does not have information on the range of size, while function F is not directly involved in the vulnerability. The fundamental cause of these limitations is that they do not take into account the semantics of vulnerabilities. So our solution aims to address these limitations by capture the semantics of vulnerabilities with safety properties, and then use these safety properties to generate vulnerability patches. We propose an approach called SYNCs that uses human-defined safety properties to generate vulnerability patches. A safety property is designed specifically for one type of vulnerabilities. For example, given a safety property for buffer overflows, SYNCs can generate patches for buffer overflows in many different target programs. SYNCs generates source code patches that can be easily adopted by developers. A SYNCs patch is in the form of an if statement that would divert program execution to error handling code when a safety property is violated. And here, we call this checked condition as a patch predicate. A safety property defines an invariant to prevent a type of vulnerabilities. For example, by the definition of buffer overflow, we can define a safety property for buffer overflows that would check between the range of size with the bounds of the target buffer. As long as the range of size is within the bounds of the target buffer, no vulnerability can occur. By doing this, the correctness of the generated patches is enforced by the correctness of the safety properties used to generate these vulnerability patches. To generate a patch, Sinks maps a safety property to a patch predicate consisting of program expressions available in the code of a target program. For one given safety property, the code of a target program, and an input to trigger the vulnerability, Sinks executes the target code, observes where the safety property is violated, and maps the safety property to a patch predicate. For example, this code allocates the buffer via a call to malloc with the size specified by S and stores the starting address of the buffer to point above. So Sinks will map buffer start and buffer size in the safety property to buff and S respectively for this target program. Similarly, Sinks will map access range and access start to L and P respectively, because the target program accessed the buffer via a call to memcopy, with the starting address specified by pointer P and the length specified by L. Eventually, Sinks will map the safety property into a patch predicate for this target program, as shown here. To address those vulnerabilities involving interprocedural code, Sinks translates program expressions across different program scopes if needed. For this same example code that we shown before, Sinks will find that the buffer size can be mapped to P times Q in the scope of function G, and the access range can be mapped to len in the scope of H. Because function F is the common caller of G and H, Sinks tries to translate the buffer size and access range to the scope of F. By examining the arguments used by F to call G and H, Sinks will translate P times Q from the scope of G to R times C in the scope of F, and translates len from the scope of H to N in the scope of F. And by doing so, Sinks can synthesize a patch predicate and assess a patch in the scope of F. In the case when a patch is to be inserted into the body of a loop, Sinks tries to promote the patch outside the loop body to reduce runtime overhead. This requires to find out the range of exercise performed by the body of a loop. Sinks address that with two techniques. For well-formed loops, Sinks uses access range analysis to statically compute a symbolic access range for these loops. And in this example, Sinks will find that the access range for this nested loop is n times m, and then it will use n times m in the generated patch. For other loops, Sinks would use loop cloning that will clone the code of the function that contains the loop, makes the cloned code free of side effect, and then let the patch cause the cloned code to dynamically compute the access range. As shown in this example, the code on the right, we show the cloned code on the top, and at the bottom, we show the patch generated by sinks will call this cloned code at runtime to compute the access range outside the body of the loop. We built a prototype of sinks that targets 3 common types of vulnerabilities. Our prototype is built on top of LLVM and works with target programs written in C and C++. We evaluate the sinks on 42 real-world vulnerabilities in 11 widely deployed applications and libraries, which in total have over 3 million lines of source code. Sinks successfully generates patches for 76% of these vulnerabilities. To verify the correctness of the generated patches, we manually compare the generated patches with official patches. So here we show one sample patch generated by sinks. So the figure on the left shows the patch generated by sinks, where the figure on the right shows the patch that's created by human developers. And we can see the 2 patches are almost identical. Sinks does not generate patches in some cases, mainly due to 2 causes. First, sinks may not be able to map a safety property to a patch predicate due to the complexity of the code of a target program. Second, sinks may not be able to find a program scope in which all the program expressions involved in a patch predicate are available. To conclude, we propose an approach called sinks that uses human-defined, program-independent safety properties to generate vulnerability patches. The correctness of the generated patches is enforced by the correctness of these safety properties. Our evaluation shows that sinks can generate vulnerability patches for real-world vulnerabilities. Thank you, and I'm open to questions.
Do we have any questions from the audience? We actually have a lot of time left. Well, then let me start with one simple question.
Mm-hmm.
So one thing that I'm not quite sure if I understand is that what exactly is the input to your system? I understand it's some form of expression of a safety property.
Yes, that's right.
Let's say for a vulnerability, for a reported vulnerability, what exactly is the input to your system?
Oh, so we require the code of the target program, and we also require one input to trigger the vulnerability, along with the safety property. So that's basically 3 types of inputs to my system.
Okay, then a follow-up question to that is how easy or how difficult to construct or define this property given a new bug?
Yes, that's so regarding that, from our experiment, and for these 3 types of vulnerabilities that the sinks can currently fix, they are very simple to define the safety properties because we just provide some primitives for security experts to write in these expressions that is an invariant to prevent one type of vulnerabilities.
I assume that the efforts required for defining these properties would be much less than the effort required for really writing a patch to this vulnerability?
I'm not sure if, we can compare this way, because the fact is that to use sinks to generate the patches, we only need to define a safety property for one type of vulnerability once. So once a safety property is defined for one type of vulnerabilities, then we can just use the same safety property
see.
to generate many vulnerability patches.
Okay, thanks.